Welcome to the third video recording of our second class preparation session. Here we go with more examples of how to form Lewis structures because it is such an important foundational concept that you will need to be equipped with in order to make progress in your studies of organic chemistry. Let's say we have a molecule parentheses H3C3 NO. That's kind of interesting. We've got three methyl groups, a nitrogen and an oxygen. Again, each CH3, that is methyl group, is attached to the nitrogen. And so here I've diagrammed them out in their full Lewis glory. And so what do we have? We have 2 electrons on nitrogen, and we have 6 valence electrons around oxygen. How do we try to compare those? Well, we could try pairing a lone pair on oxygen with that lone pair on nitrogen. But wait a second, we cannot make a double bond between oxygen and nitrogen. And why is that? Because if we did, nitrogen would be sharing a total of 10 electrons, and that's too much for a second row atom. We can't expand their octets. There just aren't orbitals available to accept those electrons. We can do that for third row p block elements, and we'll see that here soon. So how do we solve this dilemma? Well, let's move one of those electron pairs onto oxygen and use formal charges. So if we did that, we would have oxygen possessing a total of 7 things, 6 electrons and 1 bond, and we'd have to give it a formal negative charge. Of course, it's sharing a total of 8 electrons. Its octet is satisfied. That's good. Nitrogen, in this case, has 4 bonds, which 4 things, 1 fewer than the 5 valence it would like to be neutral, so we have to give it a formal positive. Of course, in terms of sharing, it's got a full octet, and we haven't violated it. We haven't expanded it to 10 electrons. This is okay. This is called a Zwitter ion. It's an example of a molecule where you've got formal charge separation. Within that molecule, the overall molecule, of course, is neutral. So that's why we have it written up here, H3C3NO. There's no net charge on that molecule. It's neutral. However, wow, there are formal charges within the molecule. It's kind of a neat idea. Let's try the same experiment with the atom that falls below nitrogen in the periodic table on that column. So CH3,3PO. Triphenylphosphine oxide. Well, we could write the same sort of Lewis dot structure where we've got charge separation as Zwitter ion. It's kind of interesting. You can drop a lone pair to form a double bond between the oxygen and the phosphorus. This is a valid resonance form for this triphenylphosphine oxide. This time it's okay. So why? Why is that? Well, phosphorus has third row d orbitals that are available to accommodate an expanded octet, so more than 8 electrons. So if we counted the number of electrons phosphorus is sharing, 2, 4, 6, 8, 10, that's okay this time because it's not in the second row of the periodic table, it's in the third row on the p block side. The other atom where you will see that that is possible is sulfur. So here we have 2 methyl groups on a sulfur, which is also bonded to 2 oxygens. It can also have an expanded octet. Here sulfur is sharing a total of 2, 4, 6, 8, 10, 12 electrons. Of course, there are other resonance forms where you might form formal charges on the atoms. In this one, sulfur has a formal positive charge. This oxygen has a formal negative. Sulfur is sharing 10 electrons. You could also do the same procedure for this double bond between sulfur and this oxygen on the bottom of the molecule. You can move a pair of electrons onto the oxygen. Now you have each oxygen with a formal minus, and sulfur has a formal 2 positive charge, and now 8 electrons. This is probably a pretty good description of this molecule in terms of what kind of charge distribution you would expect to find in it. The sulfur is less electronegative than oxygen. It will be have more of an electropositive character, and that is a greater delta positive associated with it. Carbon, however, is in the second row of the periodic table, so it cannot have an expanded octet. Let's take the formic acid anion, so formate anion, and we can move this formal minus charge from this oxygen over to this other double bonded oxygen in a rational arrow pushing sense. Why is it that we have to do 2 arrows? Well, if we stopped after just 1 arrow, why is that not acceptable? Where we've done just 1 of these arrows and transferred this formal minus from oxygen to carbon. Well, in this resonance form, we've got 2, 4, 6, 8, 10 electrons on carbon. Carbon cannot have an expanded octet. It's not like sulfur or phosphorus. So, if we do this first arrow, we have to simultaneously do the second arrow to reach the second resonance form. This brings up an idea of a resonance hybrid. You could think about that electron density spread out over those 3 atoms. Maybe each oxygen has a sort of -1/2 character to it. Of course, many chemists like to write one resonance form or the other, so we tend to write one extreme or the other. Here is something called the allyl cation. It's something we spend a good deal of time on in the second semester of organic chemistry at the very beginning. And you can see we've got a formal positive on this carbon, and we simply need to move over one of these double bonds between this middle carbon and the rightmost terminal carbon to now go between the middle carbon and the leftmost terminal carbon. If we do that, then the rightmost carbon has only 3 things, and we've got to assign the formal positive to the rightmost carbon. And so, again, we could think of a resonance hybrid where each of the terminal carbons has a positive half character, although, like I said, we tend to write one or the other extreme. How do we justify our notions about these ideas? And we actually do this through experiments. So, last idea for this video. And so here's allyl bromide. Now, I have not written all the hydrogen atoms explicitly. This is an example of bond line, which we will talk about here soon, versus Kekulé structures, where we symbolize each point on this carbon framework as a carbon. And of course, carbon can be bonded to 4 things, so we know that this carbon atom that my pen is pointing to has a bond to bromine on the right and then a bond to another carbon on the left, so it must have 2 hydrogens. This carbon on the very far left has a double bond to the carbon in the middle, so we know that it must have 2 other bonds, and those are 2 hydrogens. Well, allyl bromide is kind of interesting. If you put it in water, it will fall apart. The bromine will come off as bromide and will create our allyl cation. If you're tricky about the way you've synthesized your allyl bromide, you might be able to label the terminal carbons, say make one carbon the 13 isotope and the other carbon the 12 isotope. Well, if our ideas about resonance are true, we won't just be limited to the resonance form where we've got a formal positive on the C13. We'll also have some form of this allyl cation where the formal positive is on C12. It just so happens that in water, when we put allyl bromide in water and it breaks down, the water molecule itself, the oxygen atom, can form a bond to our cationic carbon center. This is an example of an SN1 reaction, and we'll talk at length about this type of reaction shortly. Once the water has added in to either side, either the C12 or the C13, if resonance is real, we could think about removing one of the 2 protons to it, and then we generate something we call allyl alcohol. If resonance is true, we should expect roughly equivalent amounts of allyl alcohol where the oxygen is bonded to the C12 isotope, just as well as the C13 isotope, and that is actually what we see. So this helps reinforce our ideas about resonance through experimentation, and so we're pretty lucky to use experiments to help justify our notions. That's what we do as scientists. So that ends this last video for our second class period.